All right, so finally, let's speed up a little bit because the rest of it is mathematically very straightforward. So I'm gonna do it in hopefully very quickly. So let's talk about some properties of the OLS on any sample of the data, right? So let's first talk about the fitted values and residuals. So these are y hats, or what we call fitted values, and it can be calculated by having beta hat 0 and beta hat 1 because x's are observable. And then u hat are the residuals. These are the deviations from regression line, and the ordering matters. Be very careful. It's y minus y hat, not the other way around. Because if ui is positive, negative, it has some meaning. If it is negative, you're over predicting. If it is positive, you're under predicting. Okay, so it is important to be careful about the sequence. The ordering matters. Then, what are the algebraic properties of OLS regression? We say on average, these residuals are 0. So we can see that. So on average, if I take the average of these lines, it's going to be 0. So mathematically, we can prove it. This is property number 1. Then, let me start with this third one, which is easier, and then we'll go to this. So we already talked about this one as well. Sample averages of y and x always lie on the regression line. So this is also not surprising. If I have x bar, if I have y bar, it will be always on the line. And finally, what is the third property? This basically tells you something about the covariance. So if you go ahead and look at the definition of the covariance between x and u, you see it was expected, well, the second version was, if you go and review the statistics lectures, see, it will be, at the end of the day, it will be a function of expected value of ux minus expected value of x multiply expected value of u. This expected value of u is 0 at the end of the day, so we can cross out the second part, and this is what we see. Expected value of ux is going to be a summation of this ux multiplication of these ux's. And what is important here is that, remember, this is suggesting the correlation or the covariance, that's the same, if it is 0, right, between deviations or residuals and regressors, the x's, are always 0. But this is also really important. So we're going to say that algebraically we can prove that the correlation between x and u hat is 0. All right, now let's talk about decomposition of the variance of y. So this y can be wage, can be salary, can be, I don't know, you name it, your GPA. It can be something that you want to predict at the end of the day, right? And we already know all of these things, but let's give them some even more names, right? So let's look at this observation xi. And for xi, we have a corresponding value of y. So xi and yi. This is my yi, right? So this is point xi, yi. So this is the true data. This is a true observable data. Then we're going to use OLS. OLS is going to give us back this black line. And so with that black line, the predicted value for y is going to be y hat. Okay, so this dot is going to be xi and y hat. This is y hat I. This dot is going to be xi and yi. I hope that you're seeing, you're getting the difference. And we already defined the distance between the two. We said that the distance between y and y hat is going to be u hat I. Okay, right? So this distance is going to be my u hat I. Okay. What we are interested is, in terms of the composition of the variance of y, we want to say that how far each observation is from the average of those wages. So for instance, if I have a bunch of y's, it comes with x and y, right? I want to see if the average of y is here. I want to see how far each observation is from the average. So let's show this average with a line, horizontal line. So this is going to be my average line. And we want to see how far each true observation is from that y bar. This is what we eventually want to explain, okay? And so we can decompose this thing, this blue curly bracket, into two parts. One part is, let me actually use black, and then I can refer them to their Maybe I can change this to black. All right. So what is this part? This black part is the distance between y hat, which I just calculated, and y bar, right? So I have three things: y hat minus y bar, y minus y bar, y minus y hat. Okay. The intuition is very straightforward. At the end of the day, I want to explain this: y minus y bar. Some part of it is explained by the model. Do you agree that y hat minus y bar is explained by the model? So the model is able to capture this part, this black part of the entire blue curly bracket here. And the red part is unexplained, right? So we call this one the unexplained part, unexplained. And this part, the explained. So the deviations from the average of y is going to be explained by two parts. One is the part which is explained by the model. The other one, the part that the model was off. The model was not able to explain that, right? Now, with these things, let's define three equations. We call them measures of variation. So SST, SSE, SSR. These are important, pay attention. So SST stands for sum of square total. SSE, sum of square explained. E stands for explained. SSR, sum of square or residual, and this is unexplained. Okay, so in some other textbook, they show that with TSS, I'm going to erase it. Just watch the video and then I'm going to erase it because it's a big source of confusion for students. So in some other textbook, they call it TSS. Unfortunately, they call this one SSR and SSE. So this is very confusing, I know, but I think so. If you're taking a course from MIS, maybe it depends on different people use different textbook, and I have had students that say, okay, what is SSR? Is it sum of square regression or sum of square error? That's the sad part, right? So in this course, we're going to stick to Wooldridge notation. However, please, because it has happened before, I need to emphasize. I have had students that say that, okay, my econometric students from other department is wrong. He say SSE is this. No one is wrong here. No, depending on how we define our variables, we can interpret them differently. In this course, I'm going to stick to the notation of Wooldridge, and in Wooldridge, we are going to use SST, SSE, and SSR. And this E stands for explained. And R stands for residual. Just remember, at least for my course, learn it this way. But if you're using it for other course, be careful how SSE and SSR are defined. People use E for error instead of explain and R for regression instead of residual. In this course, we're going to stick to this one. So what does it mean? Sum of the square, starting from here, sum of square total. So this is the total sum of square for the so this is our total variation that we want to explain. Y minus y bar, right? Remember, y minus y bar is the total variation that I wanted to explain. This one, this blue big curly bracket, y minus y bar. And I have to square them for the reason because if I don't square them, it's positives and negatives are going to cancel out each other. So we always square them and we add them together. So this represents total sample variation in y. We want to explain this. Some part of it is explained by the model. Some part of it is unexplained. The part that is explained by the model, we can summarize it as SSE, sum of square explained, or explained sum of square. This represents the explained part of the variation of y. And this represents the unexplained, the residual part of the variation in R, in Y, right? So think about it. Does it make sense if I write SST is equals SSE plus SSR? That's exactly what's going on. So we call this decomposition of the variance of Y. And so it says that the total variation depends on the part which is explained and the part which is unexplained. So we have to add them up. So this is what we see in the next slide. So decomposition of total variation. Total variation is consists of two parts: explain, unexplained. And so why do we need all these things? Because at the end of the day, we want to see if our regression line is a good fit or not. So we call it goodness of fit, and we show it with R-square. So R-square also, we also call it coefficient of determination. So at the end of the day, I want to see, I have some variations in Y, right? And I want to see this model, how good or bad is this model? So this model is going to be, so I can calculate the R-square. It seems that, this line is a very good fitted line, so R-square is going to be high. But if for some reason, I know the model does maybe, I don't know, maybe we are not using OLS. So this is what OLS is generating. Maybe we are not using OLS, and I'm going to use for black dots. I say, okay, this maybe is the better fitted line, not using OLS. So the R-square for this is going to be small, right? And again, we're going to talk about this thing in more detail, but we're going to stick to the OLS, which is the best estimator. But R-square is high or low. It means that better chunk of the variation in Y is explained by the model, or less chunk of the variation of Y is explained by the model. And I think if you had no idea of how do we define R-square or goodness of fit for the model, with this example, you can come up with your own statistic. If I give you 3 models, or 2 models, let's keep it simple, 2 models, and I say SST, SSE. Model number 1, total variation in both of them, of course, is going to be constant, right? Because I have one wage, and the total variation in wage is going to be constant. But I have model number 1, model number 2. Model number 1, the explained part of the variation is 80. Model number 2, the explained part of the variation is 40. Which one is better model? Obviously, saying model number 2 is a better model, right? You just calculated something like this, SSE divided by SST. So for the first one, it was 80%. For the second one, it was 40%. So this is what we call R-square. Goodness of fit, coefficient of determination, and it is defined as SSE divided by SST. What part of the total variation is explained? That's it. And if we use the equation for SSE, we can get to the second version as well. So for what do we have? So SSE divided by SST, and for SSE, I use this equation here. So I can say it's equal to SST minus SSR. Does everyone see that? Divided by SST. So I can simplify it, SST divided by SST minus SSR divided by SST, which is 1 minus SSR divided by SST. Okay. So R-squared measures the fraction of the total variation that is explained by the model. Let's look at a numerical example, and then that's it. So for our CO salary example, the R-square is going to be one of the output that you get in R. And so in this example, it's very small. It's going to be 0.01. So what does it mean? It means that only 1.3% of the total variation in salaries is explained by ROE. Are you surprised? I was not surprised because of 2 reasons. First of all, this is a very naive model. Simple regression model, we are only controlling for ROE. And secondly, I know salary, yes, it depends on ROE, but there are many, many more important factors out there that salary depends on them, not only ROE. So for that reason, I'm not surprised that the R-square for this model is small. It's only 1.3. Okay. Caution. A high R-square does not necessarily mean that the regression has a causal interpretation. This is the fun part. Do you remember? I plotted the Fetcher height versus interest rate, and the R-square was 95%. 95% of the variation in interest rate was explained by the variation in Fetcher height. What are we missing here? That's just pure correlation. That's not causation. So R-square cannot tell you anything about the causation. For causation, we need to have those assumptions. On average, the errors are 0 and 0 mean conditional assumption. So basically it means that we have to go beyond simple regression model. Okay, so I leave these 2 statements as an exercise for you guys, and I'm going to prove it in the class. But the idea is that what will happen to coefficient of r squared if I multiply all the wages to this constant? So what's the answer? And then what will happen to r squared if I multiply all the x's by a constant like alpha? So think about these things, and I'll give you some other variations as well. Actually, for your exercise, I want to think about not only the r squared. So tell me what will happen. Well, let's stop here. I'm going to talk about it in the class. All right. So this was the first class 7 of our journey in simple regression model. We're going to have 2 other classes. Class number 2, we talk about a little more detail of the assumptions of OLS. We haven't talked about them yet. And class number 3 is going to be how do we apply all these things in R. The application is going to be the easiest part. So originally you were scared of R, but at the end of the semester, R is going to be the easiest part. The harder part is the intuition of what we're doing in the class. All right, see you in next class.